All right, how's that? Can you guys hear me on Zoom now? Okay, cool. Yeah, sorry about that. Okay, so as I was saying, today we're revisiting a topic that we saw earlier this semester. So we talk about muscles again. So when you're talking about human movement as opposed to static positions, it changes a little bit of how we view muscles in terms of what they're doing, what their behavior is, what their characteristics are. So we'll be going over that today. So we'll be doing a little bit of review today in terms of the kind of the molecular structure of the muscles, what it means, what the different protein filaments mean, and all that stuff. And then we'll talk about how the muscle behavior changes as the contraction velocity changes as well. Okay. Okay. So other announcements. If you didn't get a chance to pick up your exam last Wednesday, I brought them again today. This Wednesday is probably going to be the last day that I bring the exams. So if you don't pick it up by this Wednesday, then you'll have to come to my office to pick it up. Otherwise, I'll just keep it forever, I guess. Okay. Any questions I can answer before we get started? Okay. All right. So let's go and get started. Okay. So the topic for today is muscle dynamics. Okay. All right. So like I mentioned before, we've already kind of introduced the concepts of muscle biomechanics before. So if you remember, that was maybe in the second or third week of the semester. But we're about to kind of go through muscle motion or human motion. So there's a bit more to cover once we get to this part. Okay. So first thing we're going to do, just to kind of refresh our memories, let's kind of review the structure of a muscle, starting from kind of the smallest level, which is all the protein filaments. Okay. So the main thing to know about the smallest kind of structure of the muscles is that you have two types of protein filaments. Okay, we have the actin and the myosin. Okay, and so in particular, we kind of drew a figure that looked like the following. Okay, and so on the outside here, we have our thin filaments, the actin. Okay? The actin kind of form this sheath or a pod around the myosin filaments in the middle. Okay? So the myosin filaments kind of look something like this. Okay? And then the myosin filaments had all these little tiny heads that kind of attach to the actin, kind of like so. Okay. And we have this kind of same thing on the other side as well. Okay. So in the middle here, we have, okay. And so when a muscle contracts, what we discussed before was that the myosin, with all their little, myosin heads, kind of pulls the actin towards each other. Okay. So actually, let me kind of draw it down here. So when muscle contracts, okay. And so there are two things that kind of happen when the myosin kind of pull. And so on the one hand, it generates force, and so that's kind of what we observe, when our muscles generate force to do motions or to hold a certain position. But also the muscle itself shortens as well. Okay, and the amount that it shortens is basically the combination of all these actin filaments coming closer together. Okay, all right. So this is kind of the basic kind of building block of muscle. And so, um, what you kind of view as kind of a single muscle fiber, even just a single muscle, an individual muscle that you see in the body is made up of, tens of thousands of millions of these, all kind of packed together. Okay. And so, for instance, when you look at a muscle, and I think probably the easiest way to kind of see this is to go to your local grocery store and look at kind of the meat section of the market. If you look at a certain cuts of meat, and so, usually some cuts that have very kind of prominent fibers, and so, beef kind of exhibits this a lot, is that you'll see kind of long kind of fibers that kind of run through the muscle, right? I don't know why my pencil is kind of acting up right now. Okay. So for certain muscles, you can kind of see the really nice kind of striations of the muscle kind of going like that. Okay. So each of these is a fiber. Okay. So you can't really see it, but each fiber is basically contains one of these, each of these things kind of chained together end to end. Okay. So if you remember from before, each of these units of a certain actin filament and myosin filament act together. We call these sarcomeres. I'll scroll back down in a second. Okay. So one kind of unit of actin and myosin together is called a sarcomere, and each line is a muscle fiber that contains, tens of or millions of these sarcomeres kind of connected end to end. Okay. And so what you view it, you may view it as just kind of a single line right there, but in that line, you may have, something like this, right? Where each one of these is a sarcomere. Okay. They're all kind of linked up together. So this right here is one fiber. Okay. So the reason you can't really view the sarcomeres is that they're all really tiny. So the length of each sarcomere here is about 3 microns. Okay. So 1 micron is about 10 to the minus 6 meters. Okay. It's about that length on average. Okay. And so if you have a muscle fiber that's a certain length, right? So the exact length of a muscle fiber depends on the specific muscle that you're looking at, right? So let's say that we have a muscle fiber that it's about, in total, the length might be, I don't know, let's say 7 centimeters. Okay. You can make an approximation of how many sarcomeres are in that fiber just by doing simple division. Okay. Okay. So if we take the total length of this muscle fiber right here, we convert it to meters. Okay. So that's 0.07 meters. That's 7 centimeters. And we divide it by 3 times 10 to the minus 6 meters per sarcomere. Okay. I don't have that number in front of me just because it's, but you can kind of easily kind of punch that to a calculator. That will tell you how many sarcomeres are in one muscle fiber. Okay. Okay. Now, one fiber is just one piece of a muscle as well. And so if you look at a particular muscle and you look at the cross section, the cross section contains a lot of muscle fibers that are all acting in parallel. Okay. And so if we do something like this, right? So let's say this is a muscle, a very cylindrical muscle. Okay. And so packed inside this muscle is lots and lots of fibers all kind of bunched together in parallel. Okay. Okay. And so from here, you can make a calculation as well in terms of how many muscle fibers are there. So typically what's usually measured in terms of this is the total cross-sectional area of the muscle. Okay. And so if we take this and we compute the cross-sectional area, okay. If we take the total cross-sectional area of the muscle, and then we divide that by the cross-sectional area of a single muscle fiber, okay? And this is gonna give us a number in terms of how many muscle fibers are packed within that muscle. Okay. So just some basic calculation, but you'll see in the homework, there's one problem I gave you in the homework where you run through these calculations and you're kind of, it's kind of surprising to see how many of these sarcomeres are in one fiber and how many fibers are in one muscle. And then you can kind of, keep that calculation going and see how many sarcomeres are packed within a muscle. And you're going to see it's in like the billions. Yeah.
When people work out, is it more that they would get more muscle fibers in there, or the muscle fibers would get bigger?
You get more muscle fibers. And so the muscle fibers themselves all have kind of a fixed size because the sarcomeres are all fixed size. And so when you work out, your body kind of generates, it uses protein to kind of develop more muscle fibers to kind of build it more in parallel.
Thank you.
Mhm. All right. Any questions on this so far? Okay. All right, so that's just kind of a quick review. Although I think last time, we didn't really look at kind of the macro view, but here we kind of went from the micro view of each individual sarcomere, all the way up to kind of the full muscle. Okay. Let's review the force length relationship. Okay. Okay. So the force length relationship basically tells us, how much force a muscle can generate based on its instantaneous length. Okay. Because it actually changes. And so depending on the length of your muscle at any given time, the amount of force that it can generate will change. Okay. And this is important because as a muscle contracts, right? So as your muscle kind of, contracts, it goes through its motion, the length of the muscle will change, right? So the muscle can go from either very long from when it's being stretched out, maybe in an eccentric motion, to very, very short when the muscle is kind of fully contracted. Okay. So I'm gonna go ahead and draw the curve for you, and then we'll go ahead and kind of describe its trends. Okay. Okay. So the curve looks like the following. So on the vertical axis here, we have force. Okay. And so the height of the graph there is going to tell us how much force the muscle is generating per length. And we're going to look at this in terms of a single sarcomere. So this is on the x-axis here, we have sarcomere length. Okay. And so this curve here kind of it looks like kind of like a plateau. So there's kind of an ascending region like this. Okay, so there's a region where the plot is coming up. There's a portion of the graph where it is flat. Okay. And then there is a descending portion that's slightly smaller slope. Right. So the way I drew it here, it kind of looks like it almost kind of looks like a parallel image, but the downslope is slightly less than the upslope. Okay. Bless you. Hey. All right. And so on the horizontal axis here, we actually have units for it. So that is sarcomere length in microns. Okay. So just because so I should have drawn the tick marks first. Okay. So the tick marks are a little bit unbalanced, but the idea is that, the maximum optimal sarcomere length is within this region right here, okay? Right, so that's about 2.2 to about 2.7 microns, okay? So when the sarcomere is kind of within that range right there, that's when it can generate the maximum amount of force. Okay, so why do we see this behavior? So why do we kind of see such a dramatic kind of change in the amount of force? Okay. By the way, this, even though this curve here looks like it goes down to zero, I've kind of shifted the curve up, and so this right here is not, it's not zero force, and so you can still generate force when your muscle is really short, and you can still generate force when your muscles are really long. It's just that, the curve just looks nicer once it's kind of down like that, right? So that's kind of an important distinction. So this does not mean. Okay. And so you can almost think of that. So the kind of the bottom, the baseline there is kind of the minimum force, and up here we have kind of the max force. Okay, but it doesn't go from zero to max. It's between some minimum and some max. Okay. Okay. So why do we have this behavior? So why is it that, we have a certain length kind of band where force generation is maximum? Okay. So the reason this is because of how the sarcomeres are kind of designed and how they generate force. And so it's basically due to how the actin and myosin kind of line up with each other at certain lengths. Okay. And so if you remember from the figure above, right, the way that your muscles generate force is that the myosin, heads attach onto the actin filaments and pull them together. Okay. Okay. So kind of based on that description right there, we can kind of infer that the more myosin heads are able to attach to the actin, the more force that can get generated. Okay. Okay. So force generation is all about, how many of these heads can attach and kind of, pull together and generate force. Okay. The thing that, I didn't really illustrate with the figure above is that as the actin kind of slide past each other, there are certain positions that prevent, the maximum amount of heads from attaching when they should. Okay. So let me kind of illustrate kind of an example for you. And so let's consider a situation where your muscle is really kind of bunched up. You're at kind of full contraction. Okay. In those situations, your actin can actually slide past each other and kind of overlap each other. Okay. Okay. So this is what it looks like when your muscle is kind of fully contracted. So normally your actin are kind of, a little bit a little bit spaced from each other so that every myosin head can attach. But there are certain situations where your actin filaments may look like this. Okay. So you may have one actin sheath that kind of goes like that, and then kind of its partner may overlap it, you know, and go like that. Okay. And so if you draw your myosin in the middle here, right? So because the actin are kind of overlapping each other, it prevents some of the myosin heads from attaching, right? So you have some heads here where, they don't really have a site to go to, so they kind of just, they're kind of just chilling. Okay. Okay. And so of course, not if not all the myosin heads can attach, that's going to limit the amount of force that you can generate. Okay. And so that explains kind of the ascending portion of our force length curve. The fact that, at shorter sarcomere length, we're not able to generate the full amount of force, and so if we're in this region right here, right? If we're in that region of the curve, what kind of the assumption there is that the actin is bunched up, so not all the myosin heads can attach. Okay. All right, and so eventually, your actin will reach a point where they kind of they kind of stop overlapping each other, and every single myosin head can attach. And so eventually, your muscle lengthens enough, and then you reach kind of this optimal region right here. Okay. But then eventually, the force starts to go down again as the muscle gets lengthened. Okay. And so the other thing that can happen is that the actin can actually pull away from each other so much that, they're so far away from each other that there's nothing for the myosin heads to attach to. Okay. So let me try kind of draw that for you here as well. Okay. So let's look at a situation where the muscle is fully extended. Okay. And so in this situation, your actin may look something like this. Right? So the muscle is extended at this point, so the sarcomeres are kind of pulled apart. And so if you draw the myosin kind of in the middle, Okay. There are a bunch of myosin heads in the middle right here that just aren't able to attach to anything just because the actin are all kind of pulled apart. Okay. And so in this situation, the myosin that aren't attached, they can't participate in the force generation. Okay. So that's what's happening on the descending portion of the force length curve. And so as the muscle kind of gets more and more extended, the actin get further apart from each other. And so not all the myosin heads can attach. Okay. So in this portion right here, the actin get too far apart. Okay. So that's kind of the explanation of this curve. And so, with this curve, you have an ascending portion where you can't deliver optimal force. You have a descending portion where, your muscle can't deliver optimal force, but then there's kind of a sweet kind of Goldilocks region in the middle where the actin kind of line up perfectly with the myosin head where you can generate kind of the most force possible. Okay. So this theory, this curve right here has been experimentally observed. So scientists have kind of observed this and measured this, and it's pretty much kind of flawed at this point. But the theory of relating that curve to the different myosin and actin lengths, this is known as sliding filament theory. Okay. So of course, this is kind of very simplified version of sliding filament theory, but it kind of gets the main point across that depending on the relative positions of the actin filaments and the myosin filaments, that's going to affect how much force your muscle can generate. Okay. Um, right. All right. Any questions on this? Okay. All right, so that curve that I just showed you up there, the force length relationship, that's strictly for just active force, right? So when your muscle is actively trying to generate force, the amount of force that it can generate is limited by the total length. Okay. There's actually another way that your muscle can generate force that we talked about before. Okay. And so if you remember from before, we talked at length about the fact that muscles are elastic solids, right? And so the way that we describe it is that, muscles can passively generate force through its elastic properties. Okay. And so this also has a curve. 'Cause, 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 All right. So we have the passive force. And on the x-axis here, we have the sarcomere length again. Which is again measured in microns. Okay. So the interesting thing about muscle is that it mostly exhibits most of its elastic properties in tension. So normally for an elastic solid, if you kind of compress it, there's kind of an internal force that kind of pushes it outwards. Muscles don't really experience that all that much, and so the only region where you see kind of elastic behavior is when you stretch a muscle beyond its resting length. Okay, so this passive force curve actually is mostly zero up until the point where you kind of start to exceed that optimal length. Okay, and so at about 2.7 microns, this passive force curve kind of starts to shoot up like this. Okay, right. So basically, once you kind of pass that resting length, then the passive elastic properties of the muscle start to generate force. Okay. So that's all that this curve here represents. And so, up until you reach kind of that resting length, there's no passive forces that are generated. But then, once you kind of get past that, then, the muscle is going to want to return to its resting length. And so more and more of these passive elastic forces are kind of built up within that muscle itself. Okay. So when you combine this passive force length curve together with the active force length curve up here, okay, and you actually start to see some really interesting kind of behavior. And so the total amount of force that a muscle can generate is a combination of both the passive force length curve, which is the one right here, and the active force length curve, which we showed above. Okay. Okay. All right. So once again, one more graph here. So once again, on the horizontal axis, we have the sarcomere length, okay, given to us in microns. And on the vertical axis here, we have the total muscle force. Okay. Total muscle forces, we're just taking the sum of the active and passive components. Okay. So actually, let me draw the active and passive components first. Okay. So the active component, we kind of saw looks something like this. Right? Okay. Whereas the passive component looks something like this. And so it's mostly zero. And then once you kind of get past this point right here, it starts to become upwards. Okay. Okay. So if we just take the sum of these two, we get something like this. And so on the lower regime, there's no passive force that's being generated. Okay. And so the total force at this point is just going to follow the active curve. Okay. Things start to get interesting once you kind of reach this kind of threshold of about 2.7 microns. Okay. And so right at 2.7 microns, there's a little bit of a dip, okay? Just because the active component starts to kind of fall off a little bit and the passive component hasn't really picked up, okay? But then eventually, the graph will kind of come up here like that. Okay? And so kind of in black right there, I'm showing you the total force where, the only real area of this graph where you kind of have minimal force generation is when your muscles are all really kind of bunched up and fully contracted, okay? Because after a certain point, the active component of the force does die down because of sliding filament theory, but then eventually the passive component will pick it up again, okay? So this right here, you know, this kind of confirms our kind of earlier observation where, if you want your muscles to generate a lot of force, the best thing to do is to try to extend it and stretch it as much as possible, because then you get a lot of help from the passive elastic components. Okay. Okay. All right, so that's kind of the graph right there. So kind of again, the only position where your muscles are really struggling to generate force is kind of at the left-hand side of this curve when your muscles are all kind of really bunched up and fully contracted. Okay. All right, any questions on this? Okay. All right, so that's the force length relationship. Let's talk about force velocity relationship. Okay. So similar to the fact that the amount of force that your muscle can generate depends on its instantaneous length, the amount of force that your muscle can generate also depends on how quickly it's contracting as well. Okay. And this is particularly relevant for motion because when the human body is in motion, your muscles are contracting in real time, and so it has a certain velocity. Okay. So generally what you're going to see is that as the velocity increases, so as the muscle contracts faster, that's going to limit the amount of force that it can generate. Okay. You kind of clear up the right up there. So the faster you're contracting, the less force that gets generated. Okay. The reason for this is actually quite interesting. Okay. So, going back to our kind of our sliding filament theory of, the amount of myosin heads that can attach to the actin, that can generate more force. Okay? What tends to happen when you increase the contraction velocity is that, the myosin heads just don't really get a chance to attach. Okay. Okay. It does take your body, a little bit of a split second for those myosin heads to attach. So there's a little bit of a delay in terms of, when your brain sends the signal to your muscle to contract, there's a little bit of a chemical reaction that occurs in terms of, what the nervous system actually releases. So, it's actually a chemical process of the nervous system releasing some certain chemicals, a lot of calcium into your muscles, and then that tells the myosin that they need to attach. But that process actually takes just a little bit of time. So when your muscles are kind of contracting very quickly, not all the myosin heads really get a chance to attach, and that limits the amount of force that you can generate. Okay. So the force velocity curve actually looks something like this. Okay. And so on the horizontal axis right here, we have the contraction velocity. Okay. And we're going to focus on the right side of this curve right at first. Okay. So the right side of this curve is what we call concentric contraction. Okay. And all that really means that, the amount of force that gets generated is in the same direction as the velocity. Okay. Okay. So concentric contraction, all that really means is that, the muscle is kind of actively causing a force. Okay. So the force is used as kind of like an actuator. Okay. So the force is generated in one direction and the velocity is in that same direction. Okay. So the vertical axis right here, that one actually is going to be zero. So the kind of where the origin is, that's going to be zero velocity. Okay. And the length on the vertical axis here is the force generated. Okay. So the maximum force that actually can be generated is right at zero velocity. Okay. And then it kind of just decreases exponentially from there. Okay. So this point right here, where your muscles are not moving at all. And so your muscles are generating force, but there's no velocity. Okay, so you basically have a static situation. We call this the isometric maximum force. Okay, so it's the theoretical maximum amount of force that your muscles can generate when every single one of your myosin heads are fully engaged and there's no motion. They're all just kind of just there resisting, basically. Okay, and so we give a symbol for this. And so this is called F0M. Okay. And that kind of denotes the isometric maximum. Okay. Okay. So the faster your muscle is contracting, the less force that it can generate. Okay. Now this term right here, isometric maximum, it's a little bit of a misnomer. It's a little bit misleading because your muscle can actually generate more force than that. And that's what happens when you're on the other side of this curve. Okay. So the other side of this curve is what we call eccentric contraction. Okay. And so eccentric contraction is basically what happens when the force that's generated is opposite to the direction of the velocity. Okay. So this is usually a situation when your muscle is acting against a very large external force, and that large external force is kind of forcing your muscle to elongate, kind of against your wishes. So you're kind of doing everything you can to try to resist it, but that external force is so large that it's causing your muscle to extend anyway. Okay. So the way that we kind of describe this is with the negative velocity. Okay. And in this negative velocity regime, you'll actually see that the amount of force that you can generate is actually higher than the isometric maximum. Okay. So it almost kind of looks like a mirror image curve of what's on the right side, except it's going upwards instead of down. Okay. All right. So normally, this is a fairly rare situation. You don't really find yourself in that situation unless you like to lose at arm wrestling for some reason against a lot of people. But generally, you're only kind of concerned with the right side of this graph, and so that's why we call it the isometric maximum. Specifically speaking, your muscles can generate more force in this. Right? And the reason that you have more force again kind of goes back to the fact of the elastic properties of your muscle. Okay. Because not only do you have the effect of all of your myosin heads being maximally engaged as much as possible, but your muscle is also lengthening at the same time. So you have these elastic muscle forces that are kind of ramping up as the velocity ramps up as well, including your myosin heads kind of being engaged as well. Okay. Okay, but generally that's kind of a rare situation. So most of the time you're just on the right side of this curve. And so the thing to remember is that when your muscles are not, they have no velocity, so you're in isometric contraction. That's the maximum amount of force that you can generate. And then as the velocity goes up, or the speed goes up, then the amount of force goes down. Okay. All right, any questions on this? Okay. All right, so last thing I want to discuss today. And the last thing about muscle kind of in general is there are 5 properties of individual muscles that kind of dictate its performance or how much force each individual muscle can generate. Okay. So I'll call this kind of the 5 properties let me call this 5 properties of individual muscles. Okay. All right. So all the curves that we talked about earlier today, those are curves that are defined on the level of the sarcomeres. Okay. Okay. But one thing we know is that every individual muscle in your body, whether it be your biceps or your triceps or your hamstring muscles, all these muscles vary quite extremely in terms of the size and shape of their muscles. Okay. So some muscles have a thicker cross section, some muscles are longer than other muscles, okay? And so the idea with these five properties is to take what we know about the sarcomere behavior, the force length curve, the force velocity curve, and then, modify those curves to, for individual muscles, okay? Because the dimensions of the muscle themselves will basically affect the behavior of where these muscles lie on these particular curves. Or I should say they change the shape of the curve. Okay. So we'll start going over the properties today. We may not get through all five, but whatever we don't finish, we'll finish up early on Wednesday. Okay. All right. So the first one is very closely related to the force length curve. And the number one property here is the optimal fiber length for the muscle. Okay. So we call this LO. Okay. So remember, we discussed at the beginning of class today that a single muscle fiber consists of, millions and millions of sarcomeres kind of connected end to end. Right? Okay. And so when we talk about the optimal fiber length, that's the optimal length for the entire muscle fiber itself, not for just the sarcomeres. Okay. I apologize. It looks like my Apple Pencil is kind of on the fritz right now. Okay. All right. So how do we determine this? So if we refer back to our force length curve, right, we saw that the optimal length for a given sarcomere for generating force is between 2.2 and 2.7 microns. Okay. And so if we know that a muscle fiber is just, tons and tons of these sarcomeres kind of attached end to end, then the optimal fiber length is just going to be a multiple of these of this length right here. Okay. And so the formula right here is actually quite simple. And so the optimal fiber length of a muscle, LOM, is given by N, okay, where N here is the number of sarcomeres within that muscle fiber. Okay. And then we're going to multiply that by that range, 2.2 to 2.7 microns. So of course, if you know this optimal fiber length, it's a range, although most of the time people just kind of take the average. And so the average between those two is about 2.45 microns, okay? But technically speaking, the optimal fiber length for muscle generation is within that range right there, okay? So you take the range 2.2 to 2.7 microns and you just multiply by N, okay? Okay. And so, of course, you know, the higher N, the higher number N that you have, the bigger range of optimal fiber lengths that you're going to have as well. Okay. So what are muscles that have higher numbers of sarcomeres? Well, a sarcomere is a fixed length. And so if you have a muscle that's just naturally longer than other ones, you know, the longer muscles are going to have higher values of N. Okay. So relatively long muscle, you know, the ones that kind of come to mind are the muscles in your limbs, technically. So like your calf muscle, your quadricep muscle, your hamstring muscle, your bicep muscle, all these are fairly long muscles. So they're going to have high values of N compared to some of the shorter muscles in your body, like maybe your deltoids. Your deltoids are kind of a very packed muscle. Okay. Now, the interesting thing is that for your longer muscles are going to have a longer plateau region in the force length curve. Okay. Okay. Because remember, the optimal fiber length here is a range, right? And so between 2.2 to 2.7 microns, that's about 0.5 microns of range. And to the higher number of your N, you know, that range is going to get higher as well. Okay. And you actually, so you actually kind of see kind of a very interesting phenomenon. Okay. And so once again, I'm going to draw a force length curve, but this force length curve is going to be a little bit different. And so instead of the sarcomere length being on the horizontal axis, I'm going to label the horizontal axis as a total fiber length. So we're talking about a whole muscle fiber. Okay. So remember, a muscle fiber usually runs from one joint to another. Okay. Okay. And what I want to compare here are the force length curves for a long muscle versus a short muscle. Okay. The vertical axis again is going to be force. Okay, so for a relatively short muscle, you know, a short muscle is going to have a relatively narrow kind of plateau region, and it's going to be shifted to the left because you know the lower bound of the optimal fiber length is going to be lower. Okay, and so for a shorter muscle, you know, your curve may look something like this. Okay. So you have a very narrow kind of plateau region and the entire curve is shifted to the left. Okay. Whereas if you compare that to a long muscle, okay, a long muscle is going to have its curve shifted to the right here, and its plateau region is going to be slightly longer. Okay? And so a long muscle might look something like this. So I'm exaggerating this a little bit just so that you can kind of see the differences, but this is kind of what you can kind of expect. Okay. Okay. So a long muscle again has a wider plateau region and the entire thing is shifted to the right. Okay. The reason for the shift to the right is remember, the lower bound or optimal sarcomere performance is 2.2 microns, right? If you have a higher number of N, higher sarcomeres that are attached kind of end to end, that's going to push your lower bound over to the right as well. Okay. And so this is also going to affect the force velocity curve as well. Okay. Okay. And so in terms of the force velocity curve, um, it's going to increase the amount of velocity, or the longer your muscle is, it's going to increase the or I should say this. So the higher your N value is, the longer your muscle is, um, it's going to decrease the decay. Okay. And so your muscle is going to be able to activate or act with a greater amount of force at higher velocities. Okay. That was a very difficult kind of messy way to explain. You'll see the curve is just higher than the other one. Okay. 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 So the main point and kind of one of the main points I'll kind of leave you guys with the lecture today is that for a longer muscle, longer muscles just have more sarcomeres connected together in series. Okay, so the chain of sarcomeres is just longer. And so when you have a longer series of sarcomeres, it's going to kind of change the behavior of the muscle. Okay. Okay. And so if we draw the force velocity curve, I'm just going to draw the right side of the curve here. Okay. And so right here, this is velocity. And up top here, on the vertical axis is the force, okay? For a long muscle, so both long muscles and short muscles typically start at the same isometric maximum. Well, it depends on the cross-sectional area. We'll get to that, and that's one of the other properties. Okay? But a long muscle will typically decay a little bit slower, like this. Okay? Whereas a short muscle will have their behavior kind of decay more quickly, something like this. Right? And this difference of behavior is purely just due to the difference in the sarcomere mix, okay? Or the amount of sarcomeres that these muscles have. Okay. All right, any questions on this? Okay, let's stop here for today. I don't want to get into the other four properties until next time because each of them are kind of a little bit of a journey. So we'll stop here. If you didn't get a chance to pick up your exam yet, I have them here today. Remember, Wednesday is the last day that I'm going to bring the exams to the lecture. And so if you don't pick up your exam by Wednesday, I'll still have them. I'm not going to throw them away. They'll just be in my office, so you just have to come to my office for them. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your day. and I will see you guys on Wednesday.
That's one question. When you put E slash W.
Oh, it's between.
Okay.
Yeah.
Because I was looking up, so I guess I missed when you said that. I'm
Yeah.
like, black and white. That doesn't make sense.
Yeah, between's a long word, so I just say B slash.
That's anything else.
You too.